What I want to talk to you about today is a puzzle. And my favorite version or description of this puzzle comes from Peter Winkler's beautiful book, Mathematical Puzzles, A Connoisseur's Collection. Here's how the puzzle works. We have 4 identical unlabeled switches wired in series to a light bulb. What this means is to turn on that light bulb, you have to turn on all 4 of those switches at the same time. The switches are simple buttons whose state cannot be directly observed, but can be changed by pushing. They are mounted to the corners of a rotatable square. At any point, you may push, simultaneously, any subset of the buttons, but then an adversary spins the square. Show that there is a deterministic algorithm that will enable you to turn on the bulb in at most some fixed number of steps. If this sounds like a Martin Gardner puzzle, it is because it essentially is. In Mathematical Games in February 1979, Martin Gardner describes this puzzle called the rotating table, which has some different details, but it has essentially the same principles in it. But what I want to talk about today is the Peter Winkler version of the puzzle. And it turns out that this is a beautiful, fun puzzle to think about, and I'm not going to tell you the answer today. But instead, what I want to do is take a page out of Polya's book and really embrace the principle. If you can't solve a problem, then there is a simpler problem you can solve. Find it. We could go to a one-switch puzzle. That's the simplest one. And we all did that this morning when we turned on the light in our hotel room. And so what we're going to do instead is we are going to talk about a 2-switch puzzle. Here we have 2 switches. They're mounted on the corners of a rotatable rectangle. And we're going to solve this one together real quick. Here's our strategy. We're going to first start by making an assumption. And the assumption is that both of the switches are turned off. This assumption might not be right, but we can check it by pressing both of the buttons. Since the light bulb didn't turn on, that means that one was on and one was off. The adversary spins the table, and we try and guess the one that is off. Doesn't turn on the light bulb when we guess, so that means we guessed wrong. But now we know that they are both in the off state. We can have the adversary spin, press both of the buttons, and it guarantees that we turn on the light bulb. Very cool. So let's ratchet this up. Let's do this on a triangle. But there's a problem. It turns out that there is no deterministic algorithm for solving this puzzle on a triangle. On a pentagon, we're still out of luck. On a hexagon, maybe it's an even thing. On a hexagon, we're out of luck as well. And you might think about why that might be. We could also imagine that the adversary can kind of just wiggle the switches around. They're sort of placed on a table. And when they do that, that won't turn on the light bulb. There's no deterministic way to turn on the light bulb there either. But there are other generalizations we can solve. We can do this on an octagon. We can do this on a square where one of the switches is distinguished. We can even do this if we allow what group theorists call dihedral action, which is not only do we rotate the square, but we also might flip it. We can still guarantee that we turn on the light bulb. So I was thinking about this problem in about 2018, and I was at a math conference, and I had figured some things out about it, and I thought, okay, well, this problem is solved. We're sort of out of luck on the triangle. And then I was falling asleep one night, and I thought, wait a minute. What if we had different kinds of switches? What if instead of being on, off, we had something that went on, off, off? And if you do that, it turns out, then you can solve the puzzle on a triangle with these special kinds of switches. And this result was published when I was 1 year old. And generalizing this puzzle became a part of my PhD dissertation. So we go to the next month of Mathematical Games. And Martin Gardner mentions this anecdote. He says, Ron Graham and Percy Diaconis, who are 35 and 45 at the time, have ways of generalizing the problem by replacing the glasses, what we're calling switches, by objects that have more than 2 positions. Martin Gardner suggests that this leads to some deep combinatorial questions that, as far as he knew, hadn't been explored. And I agree, deep combinatorial questions that hadn't been explored. So here's a funny kind of switch that we might deal with. We might make a switch that I don't recommend you install in your bedroom, where we have 3 different pieces to the switch. The pieces are identical, and in order to turn on the light bulb, you need to put them in sort of the right order to complete the circuit. If we have 2 of these funny switches on a rectangle, then it turns out that we can actually guarantee that we can solve this light bulb. And the reason for this is that, well, we can model this using some ideas from group theory. And the idea is that we can always do nothing to a switch. That's one of the group theory axioms. We can always turn on the light from any given state if we sort of make the right lucky guess. Those are our inverse elements. And then we want to have not horrible switches, so we steal that fourth axiom. And Sarah Hart gave us some really great examples of groups. But more importantly, she said what we all wanted to say, which is that group theory is the best thing in mathematics. Now, my talk has the word Wreath products in it, and what that comes from is this kind of complicated construction in group theory. And when I teach this construction, I teach students don't think of puzzles as Wreath products, but think of Wreath products as puzzles. And so what we can do is we can model this Wreath product in exactly this way. Now, the very last thing that I want to tell you is that it turns out that you can do this on a particularly famous group, which is 2 copies of the monster group. The monster group is this huge set of symmetries that has 10 to the 53 different symmetries. But if you want to solve this puzzle, it's going to take more than 6 times 10 to the 107 moves. So you better get started right away. Thank you so much.